Pluto is a distant and confounding minor planet, once considered a part of our planetary group's planetary family. However, recent alarming announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an amazing revelation. They suggested that this chilly world is on a collision course with Neptune. Yet how could this happen, and what might be the results of such a significant event? Are we seeing an intriguing cosmic eccentricity, or is there something else to this approaching limitless effect? Pluto, a former planet that was reclassified as a dwarf planet, remains an enigma due to its odd orbit. It continues to be a subject of interest and study in the astronomical community. According to recent expectations by leading specialists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two bodies, which could represent a critical risk even to Earth. Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an unbelievable 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. However, the interest doesn't stop there. Pluto's orbit is marked by an astoundingly curved shape, straying significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination of 17 degrees to the ecliptic plane. The course Pluto follows is much steeper compared to other planets. One of the most fascinating aspects of Pluto's orbit is its crossing point with Neptune's. For approximately 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, challenging what we'd expect from their positions in the solar system. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to determine its unique orbital path. Unlike other planets whose orbits lie mostly close to the ecliptic plane, Pluto's orbit stood out due to its steep inclination and elliptical shape. The mystery deepened when scientists realized that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is proof of the intricacies of celestial mechanics. The three-body problem in space calculating the interactions between Pluto, Neptune, and the Sun is notoriously difficult. Pluto's orbit is turbulent. Minor deviations in starting conditions can lead to significant differences over millions of years. Yet these unusual properties have been found to maintain stability over exceptionally long time scales, keeping chaos under control. Recent simulations have helped us understand how the giant planets Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Jupiter's massive gravity is strong enough to help keep Pluto on a stable path for potentially billions of years. These forces are essential in maintaining the order and consistency of celestial dynamics. Without them, our planetary system would be a place of far more unrest and unpredictability. Pluto's orbit is a remarkable illustration of celestial mechanics at work, displaying both stability and chaos. The unique characteristics of its orbit, influenced by the gravitational forces of nearby planets, especially Neptune, highlight the dynamic nature of space. Predicting major events, particularly those involving turbulent orbits like Pluto's, presents tremendous challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. While numerical simulations offer powerful tools for understanding and predicting the behavior of celestial bodies, they also highlight the limits of our predictive capabilities. Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in astronomy, have expressed concern about the possibility. If Pluto and Neptune were to collide, it would be a captivating and devastating event in our neighborhood planetary system. The impact would release an immense amount of energy, probably destroying Pluto given its smaller size and icy composition. Debris from the collision could scatter across the planetary system, potentially posing danger to other planets and their moons. For Neptune, such a collision could alter its atmosphere and possibly its orbit depending on the specifics of the crash. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings a unique perspective to the discussion. His views on the future of space exploration and the connections between celestial mechanics and theoretical physics offer valuable insights into mysteries such as Pluto's orbit. Understanding the complex gravitational interactions and orbital elements of celestial bodies like Pluto can yield important insights for future space missions. This knowledge can help in navigating the planetary system more efficiently, predicting potential hazards, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. Regarding planetary physics, celestial mechanics and theoretical physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate directly to fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that could potentially relate to string theory. String theory, a theoretical framework in which point-like particles are replaced by one-dimensional strings, aims to explain the fundamental forces and matter in the universe. The collision could create extreme conditions of energy and gravity, possibly resulting in phenomena where string theory predictions become testable. For example, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, an area of key interest in string theory. While the direct effect on Earth would be negligible due to our distance from the outer planetary system, the scientific implications of such an event could be profound. It may enhance our understanding of the fundamental nature of the universe. Pluto's confounding dance around the Sun continues to enrapture scientists and enthusiasts alike, offering a window into the complexities of celestial mechanics. Its reclassification as a dwarf planet sparked discussions and redefined our understanding of planetary bodies. Recent discoveries about its orbit have reignited interest in its role within the solar system. Neil deGrasse Tyson and Michio Kaku, two distinguished voices in astronomy, have raised concerns about a potential crash between Pluto and Neptune. Their warnings emphasize the importance of understanding the gravitational interactions and orbital mechanics that govern celestial movements. Pluto's orbit, characterized by unpredictability and steep inclination, defies traditional assumptions and challenges our view of planetary motion. Unlike the nearly circular orbits of neighboring planets, Pluto's path follows a unique course intersecting Neptune's orbit during parts of its long journey. The gravitational influence of other planets, particularly Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over time. Despite its turbulent nature, numerical simulations and theoretical models suggest Pluto's orbit remains relatively stable within the broader framework of the solar system's gravitational field. The potential for a Pluto-Neptune collision, while hypothetical and unlikely in the near term, highlights the ongoing uncertainties in planetary dynamics. It underscores the fragile balance of forces that govern celestial bodies in our solar system. Beyond its scientific significance, studying Pluto also offers practical insights for future space exploration missions. NASA's New Horizons spacecraft, launched in 2006, provided exceptional images and data of Pluto and its moons during its historic 2015 flyby. The mission revealed stunning details of Pluto's surface, including mountains of water ice and vast frozen nitrogen plains, enhancing our understanding of geological processes in the outer solar system. New Horizons demonstrated the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained insights into the diversity of celestial bodies and environmental conditions present in the outer solar system. These discoveries inform future missions to explore other dwarf planets and trans-Neptunian objects, furthering our knowledge of planetary formation and evolution. Pluto's reclassification has also sparked discussions about the criteria used to classify celestial bodies. The debate over planetary classification reflects broader questions about scientific categorization and the evolving nature of astronomical knowledge. While Pluto meets some criteria for planethood, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diverse characteristics of bodies beyond the traditional 8 planets.